last time to discuss rigid body equilibrium. So I'll just write it down. Rigid body equilibrium. So as I said, a rigid body is any structure that you can find anywhere around yourself or in the nature. And any rigid body or structure is supported externally through some mechanism that holds the structure in place and the structure is not moving or is in equilibrium. Okay? And the objective of rigid body equilibrium, which is the rest of the course, is twofold. So when we talk about rigid body equilibrium, these are the objectives. Objective number one is to find all external support or reaction forces acting on a body. Okay. What does that mean? As I said, a structure is supported by a mechanism. You're sitting on this chair, those legs of the chair are holding it in place, right? The tree is supported in the ground by its roots, and that light fixture is supported by those cables. Any structure you can think of is somehow supported. We've learned by now that all forces and all moments acting on a structure can be reduced to a single force and a single moment, which we call that equivalent system of forces moment, right? What we haven't talked about is that when you say a structure is supported and it's holding in place, what does that mean? That means there are forces that are holding the structure in place so that due to the action of those applied blows, the structure does not move. What we want to find out as a first objective, if you have a structure supported by any kind of mechanism, how to find those forces. You want to design a board or maybe a fixture that holds this board on the wall, right? So you need to know how much force each bolt will carry. You want to build cables or some fixtures to hold this light fixture in place. You need to know how much force each of those supports, being bolts or rivets or whatever, will be subjected to. So we want to find out what are the support reactions that hold the structure in place. That is objective number one in rigid body equilibrium analysis. Objective number two, any structure, at least those that we are dealing with, is made of components that these components are connected together. The chair you're sitting on is made of legs, the platform, the seat. These are all pieces that are connected together. So to design this structure, it is important to know how to connect these pieces together, weld them, bolt them, glue them, whatever, right? So you need to know, as you take these pieces apart, what are the forces that are needed to put these back, put them in one piece. The connection forces, the joint forces. So we want to find out, okay, all internal forces that keep the components together. So these are the two objectives of equilibrium of rigid bodies. We will, for the time being, focus on this. So that's the objective one. As I said, when you talk about a support for a structure, regardless of its shape, Support plays a function. That function is keeping the structure in place. So if you have a light pole, right, or a tree, okay, or a beam, these are all subjected to various types of loads, right? What is supporting them, for instance, in this case of this light pole, is what? You have something that is keeping this structure in place. Support means a mechanism that resists motion due to the application of the external loads. So if this is fixed in the ground and it is not moving in this direction, cannot be moved in this direction, and you cannot bend it in any direction at this space, what does that mean? No movement in this direction means there is then a hidden force internally that is resisting that motion. There is a force internally at this point that is resisting any motion you want to impose, like this. And there is a moment that is resisting any bending that you want to impose and move the structure. So a support like this represents three forces. So for us, yes?
Are we still looking at a point like a particle, or now as an entire body?
Now we look at the entire object, but at those points of supports, right? We look at basically what we have here. Now we're looking at the entire structure. So forces are applied anywhere. Okay. So how do we figure this out in general? In order to do that, first of all, we categorize the structures in 2D and 3D. So let's focus on 2D structures for the time being. In 2D structures, the types of motions that are prevented are very limited if you think of a structure being a two-dimensional structure, okay? I'm going to assume that this object is only moving in this plane. So although this is a 3D object, let's assume this is a 2D structure, okay? If you have a 2D structure, there are only three possibilities for a connection. That support maybe is holding the structure in such a way that rotation at the point of support is allowed. The structure, which is this one, is allowed to rotate. It is allowed to move, say, in this direction. Only the motion in one direction is not allowed, which is perpendicular to the allowed direction of motion in this case. We call this a roller. Roller doesn't mean that this is necessarily a roller, but it's a mechanism that can prevent motion only in one direction. The cable that is supporting that light fixture allows rotation, right? You can move it also in this direction, right? But you cannot pull it down. So that cable is, in a way, a roller, represents one force. So assume this is a 2D structure. Okay, motion is allowed in this direction. Motion is also allowed in this direction. You can rotate it if you want, okay? But when you sit on it, you cannot move this downward. So the mechanism that is supporting this structure is allowing motion in any direction, but resisting motion in one direction. So that support represents one unknown force. There are supports that allow motion, rotational motion, but they do not allow motion in two directions. We call them pins or hinge support. Again, we don't have a 2D thing here, but let's think of it this door, okay? you can, if you look from the top, right, just from the top, so take this cross section. The motion in that plane is allowed rotationally, right? But you cannot push this way, and you cannot push it that way at that joint. So motion in two directions is prevented. We call that a pin. A bolt is a pin connection. Yes.
Can you explain the roller picture one more time?
The roller picture is basically allows motion in this direction and allows rotation as well. Okay. A good example. I mean, here we have a roller, right?
Yeah.
The motion is allowed.
Okay.
Right? Rotation is also allowed, but you cannot push it down.
I'm just trying to visualize how in 2D it, or I don't know, I don't really get that.
Right.
But
Imagine that you have, for instance, something like this. A good example, let's say you have a piece of a board,
okay.
right? You just nail that to the wall, just one single nail, right?
Yeah, yeah.
If there's only one single nail, this board can rotate, right? Easily. But it cannot move this direction or that direction, that's a
Okay.
pin.
Okay.
Right? But if this was something like this, you had versus a sleeve or color, right? That allows motion in this direction, and you had this connected to it. So this is structure, at this point of connection, can rotate, right?
Yeah.
Can also move up and down.
Okay.
So
All right.
only in that direction cannot. Okay. Then there is another type of support, root of a tree, or this light pole in the ground that is fixed, foundation of a building, poured concrete, this is in place. Motion in this direction is not allowed, motion in this direction is not allowed, and rotation is not allowed. So we call this a fixed end support, which means there are three unknown forces and moment that are resisting the motion, rotational and translational motion in all directions. So in 2D, we have no more than these three types of connections. So we discussed what the objective is in studying rigid body equilibrium. When we talk about support system, or what holds a 2D rigid body in place, what are the possibilities for the unknown forces that do not allow motion at the point of support? Now, the next thing that comes is what is meant by the rigid body equilibrium analysis, okay? In order to demonstrate that, or discuss how we are going to achieve this objective, I'm going to demonstrate that through an example, because that's the best way of describing what we are going to do. So I'm going to start with an example like this, okay? Let's say you have a structure. This is the meaning of rigid body equilibrium, okay? Let's say you have a crane structure like this, that carries a load of 5,000 pounds. This crane structure is supported at the base through a pin, and what that pin, just to give you an idea, you've seen, for instance, in bridges or some columns, how, for instance, the type of support might be something like this. You have a plate So this column, which is a steel column, simply bolted to this plate. It can rotate, but it cannot move this way or this way. So that's what we have here, okay? Here, at this point, which is about 12 feet from this base, at this top, we have, in fact, something like this, okay? You have see, there's no bolt here. So we have a kind of a sleeve here. This can go up and down like this if needed, and it can also rotate at that point. Okay, rotation is allowed. Let's call that point B. These distances are given. This is 12 feet, and this is 8 feet, I guess. So you want to find the unknown reaction forces that are holding this plate in place. As I said, the objective of rigid body equilibrium is to find support reaction forces. So let's see how we address that objective, or how do we solve rigid body equilibrium problems. I would outline 3 easy steps that you should follow to solve any rigid body equilibrium problem. Step number 1, the easiest step. You need to set up an XY coordinate system, because we are dealing with forces and summation of forces, the equilibrium equations, and so on. And eventually we want to find the forces and their directions with respect to a set of coordinate systems. So you set that up, okay? Step number 2. This is what I call 85% of what statics is all about. Or understanding of this concept means that you have understood 85% of all you need to know to get out of this course. We are dealing with forces and moments in statics, right? Forces and moments mean what? Equations of vector equations for forces, for moments, and the fact that we know when a system or a particle is not moving, summation of all forces and all moments should be 0, right? We learned that no matter how many forces or moments acting on a system, they come down, or they are equivalent to a single force and a single moment. Whether these forces are known or unknown doesn't matter. All forces acting on a structure can be reduced to a single moment and a single force. And when the structure is in equilibrium, that means those sums have to be 0, otherwise the structure moves, right? That's the meaning of equilibrium. So equilibrium means what? Equilibrium means summation of all forces acting on the structure is 0, which implies, obviously, the x components and y components are 0, and summation of the moments. Moments are free, right? Couples are free to put anywhere. So summation of moments about any point would be 0. But this is the tool that we have. How do we apply that to find this? or just this objective. The platform, the interface, is this. You need to convert this structure, its support, applied loads, to a set of forces and moments. How do you do that? Through setting up what we call free body diagram. Free body diagram is what allows you to apply these equations of equilibrium and find the unknown forces externally acting on the structure, which is the first objective of rigid body equilibrium. But what is free body diagram? Free body diagram is this. You separate the structure or the object or the rigid body, okay, from all supports that are holding the structure in place, okay? Instead, you place the effect or the effects of these supports on the diagram of this object. Effects means forces that these supports represent, okay? You also place all applied loads or applied forces or moments. What you do or what results from this operation is what we call a free body diagram. So let's demonstrate that here. This is the structure you have. So I'm just going to cut that from anything that is supporting the structure, okay? So this is the structure, okay? Now I will put the effect of the supports back. I said this is a pin. Pin represents two unknown forces. So let's put back the effect. Motion is not allowed in this direction. Motion is not allowed in this direction. So that means there is an unknown force in this direction, unknown force in that direction. Does the direction of these forces or what the direction you choose for them matter? No. You can choose any direction you want. Once you apply the equations of equilibrium and find the unknowns, if the result is negative, that means the assumed direction is wrong. If it is positive, your assumed direction is correct. We'll see that. How about here? I said at this point, rotation is allowed, and this is kind of like a sleeve, so this beam can move along this tube. So that is a roller, which means only the motion in this direction is prevented. And that direction is a direction perpendicular to the direction that the rectilinear motion is allowed. So there's an unknown force RB there. I will also put back the applied load, and we have only 5,000 pounds here. This is the free body diagram. Once you have the free body diagram, step 2, then last step, or the final step, which leads to finding what you are supposed to do in rigid body equilibrium. Objective 1 is this. You just simply write the equations of equilibrium, which are these. So write those equations of equilibrium. So that is step 3. Summation of forces along x, 0. Summation of forces along y, 0. Summation of moments about any point is 0. You see, free body diagram has reduced the problem to just a set of forces that you have, and maybe you may have some moments too. In this case, you don't. So all you have to do, consider that all of these should reduce to a single force and a single moment, and both of those have to be zero. What is that single force? Resultant, or sum of the x and y component. What is that single moment? Moment of all these forces about any point, okay? Since summation of moments about any point is zero, and we engineers always look for the easy way out. We always look for the simplest solution. We are lazy, okay? We need to optimize problems. We start not in that order necessarily with these equations. I recommend that we always start with this equation first. Why? Because you're taking summation of moments about any point, right? So if I take summation of moments about the point of intersection of two unknowns, that is point A, that equation gives me only one unknown. So you have first one unknown, one equation. Whereas if you started with these, you have two unknowns in each equation, if not three. So I will always start with this. And in 2D rigid body equilibrium, you have no more than three unknowns. Otherwise, you cannot solve the problem because you have only three equations to solve for. So if I take summation of moments about point A, this force generates a moment which is clockwise. This is the vertical distance given as 8. So you have 5,000 times 8 negative because it's clockwise. Then you have this force, its moment about point A. This distance is 12, again turning clockwise. So you have negative 12 times RB is equal to 0. And if you solve for this, you get reaction at B that comes out to be that's 3,330 pounds. But it comes out to be negative. As soon as you see a negative sign, that means the assumed direction that you had is wrong. So you have to erase this, put the correct direction here, and then move on. So if that is the direction, this result would be then positive. Okay? So that is the answer. Now you apply the other equations. Summation of forces along x is 0. You have a net force in this direction, 3,330, RB plus AX equal to 0. That means AX is also 3,330 pounds. Okay? And then summation of forces along Y is equal to 0. Okay? So you have AY minus 5,000 is equal to 0. So AY would be 5,000 pounds acting in this direction. And that's it. So as you see, the last step is really the easiest. The most important step is free body diagram. Any questions? I'll do more problems. Let's do another problem. Let's say you have a frame like this. This is 2 meters, 2 meters here, 3 meters here. there are two forces acting on this frame. 40 pound downward, 40 Newton downward here, 60 Newton force laterally in this direction. You also have a concentrated applied moment of 20 Newton meter. The way this is supported is this. At point A, you have a pin support, and at point B, here, there's an inclined surface. You have a pin support there, connects to a roller, and this roller is acting along a surface 60-degree incline. Okay? And you want to find all unknowns, find all support, reaction, forces, which is the objective of rigid body equilibrium. Yes?
Is that the same thing that you did in the last problem? Was that the instructions for the last problem?
Same thing. You want to find all support reaction forces. That's always the objective in 2D rigid body equilibrium.
Can it rotate at point B?
It can rotate at point B, and it also moves in this direction at point B. That's in fact the whole essence of
How can it rotate?
because there is a pin here, okay? So it can rotate, but as it rotates, it can also move in this direction. So motion only in a direction perpendicular to the direction of motion is prevented, okay? So steps are, as I said, step one, you just set up the X and Y coordinate, X and Y. Step two is the heart of rigid body equilibrium analysis, free body diagram. What do? You cut the structure from its supports, replace back the effect of these forces that supports represent. This is the pin, so you have two unknowns. Again, remember, directions do not matter. Here, you have a force that does not allow motion in this direction. That's what that roller does. So this is 60 degrees, meaning this is 30 degrees, and this is R at B. Put back the applied loads, 40 Newton, 20 Newton meter moment, and 60 Newton force. This is the free body diagram. Once you have that, it's 85% or 87%, 87.5. Okay. So step three, easy. Summation, I will start with summation of moments equal to 0, and I find the location where two of the unknowns intersect, and that would be point A. So I get rid of those two unknowns. Remember, this is always the sign convention for positive. Okay? So you will never ever forget, or you're not allowed to forget, the name of a person the rest of your life. Saint Verignan. You have to respect that fellow. Okay? That means all inclined forces have to be broken down to components before you apply equations of equilibrium. That makes your life easier. So this is RB cosine of 30, which is square root 3/2. This is RB sine 30, which is 1/2. Now let's write down summation of moments about point A. So when you take a moment, this force rotates about point A counterclockwise, so you have RB half times the moment r, vertical distance from here to this line of action, which is 4 meters. Positive. This force also rotates positive about point A. Vertical distance is 6. So you have plus RB square root 3 over 2 times 6 meters. This force rotates clockwise, so it's negative. So it would be negative 40 times the moment r, vertical distance from here to the line of action, given as 2 meters. You're summing up all the moments. You do have an applied moment here also, should include it into that summation of moment equation. And that is acting also counterclockwise, and it is 20 Newton meters, and that's it. Equate all of those to 0, and if you do that, this gives you RB comes out to be 94.5 Newton, once you solve that equation. Yes?
There's also the 60.
How did I not include that 60? Shame on me. Okay, I didn't even see that force. You do have also the 60 force, which is also rotating clockwise. So it would be negative 60 times the distance of 3. But I had the answer, so answer doesn't change. Okay. All right. Any questions on that part? So you just go ahead. Summation of forces now along X equal to 0. So you have negative RB, which is 94.5 square root 3 over 2, this force, positive 60, because this was X and Y, right? And plus AX equal to 0. If you, yes?
In the moment calculation, where did the two, or how did you determine the line of action?
For 40?
For the 40 and the 60?
60. See, this is the line of action of this force, right? And you're taking a moment about this point. So it would be a vertical distance from here to here, right? And this is the line of action of this force. So vertical distance from here to here, which is this. Yes?
Does it tell you to take a moment about A, or do you use the?
No, you choose it yourself. Yeah, always, all you need to know is, what you know is that you have 3 equations of equilibrium. And you know that summation of moments about any point has to be 0. So you choose the best point, which is eliminates the one that eliminates more unknowns. Any other questions? Okay. So if you solve for this, AX, in fact, is going to come out to be, I have 21.8, and then you solve summation of forces along Y is equal to 0, so you have AY minus 40 plus RB, which is 94.5 times 1/2. Those are all the forces you have, equal to 0, and that will give you AY. And I don't have the answer for AY, you can just figure it out. Well, you can actually do that. It's almost 7, because this is almost 47.5, so almost 7 Newton. Okay. Any questions? Statics is easy, right? All you need to remember, summation of forces, summation of moments is 0 equilibrium. So as long as you know what those forces are, how to set up the free body diagram, rest is just a bunch of algebraic equations, that's it. That's it. The most important part, free body diagram. Okay. So let me do another problem. Okay, let's see, I have another good problem here. There are many good problems. I'm going to spend 2 more sessions on this topic, so we will beat that to death. Okay? Okay, I have 2 very good problems here. I will do this one first. Okay. Through this problem, I want to introduce also a very simple yet very important concept, as you will see. So we have a beam that is supported through a bolt, rivet, whatever, here in a pin support at point A, and then a straight bar like this, actually something like this, it's even better. A mechanism like this. Is supporting this structure. This distance is 1.5 meters. You have a force of 600 Newton acting on this beam in that location, 1 meter from this end, 1 meter to this pin. This is B, and then another 800 Newton force acting at the tip of this beam, and this is 2 meters.
Is that rigid?
Which one?
The B or the?
B is a bolt here.
I mean just that squiggly thing at that.
The squiggly thing, so you wanted to support this structure. So as an engineer, you were asked to, basically design some fixture that would support this beam. You go around, you don't find anything other than this ugly looking, weird piece of, I don't know, steel, bent steel piece. You say, well, this is good enough. I'm just gonna connect it to this beam, just with 1 bolt here and 1 bolt there. And the shape is weird. That's the whole point I'm gonna discuss actually. Is the problem statement clear that you have a beam supporting these loads, this moment, which is applied to it, we want to find reaction forces at the supports. Where is this beam supported? Here and here, right? That's how the beam is supported. Is that clear? This is another basic, simple, important concept that I'm gonna throw at you. We'll discuss it. If you don't get a chance to finish it and solve the whole problem, we'll continue on Friday, but let's do this. We've learned about the concept of equilibrium, right? And equivalent systems. Let's look at this. Let's say you have a structure, no matter what the shape of the structure is. It is pinned at one end, and it is pinned at another end to the rest of the world, okay? Which is what we have here. We have this weird looking piece, pin connected here and pin connected here. As we said, if these are pin connections, that means you have how many unknown forces here? The pin, you cannot move in this way or in this way, right? So you have two unknowns, right? Here and here, right? Let's say resultant of these being, this is the resultant of those unknowns, right? I call that F1. Same thing here, you have two unknowns. I call the resultant F2. And those are the only two forces that are acting on this structure. In other words, this is a structure that there's no load acting along this structure. It is only supported at these ends. And this is in equilibrium, okay? If this is going to be in equilibrium, right, that means summation of forces acting on this structure, the summation of moments acting on this structure have to be zero, right? So let's look at it this way. I will connect this end, I call that end A and B. Let's connect these two. Straight line that connects the two ends. I will resolve this force now into components along this line and perpendicular to it. Mr. Saint Verignon, where are you? So this is F2x, this is F2y, this is F1y, this is F1x. I haven't done anything extraordinary, right? So if you say summation of forces along x has to be 0. This is x, this is y. F2x has to be equal to F1x, right? And if I write summation of forces along y is equal to 0, okay, what happens? Before I do that, I will actually write, let's say, summation of moments at A is equal to 0. That's the third equation of equilibrium that I have. If I take summation of moments at A equal to 0, what happens? This goes through A, so I only have one force. F2y times this distance is 0, so F2y has to be 0, right? Since summation of y forces is 0 and F2y plus F1y is 0, that means F1y is also 0. What does that mean? Yes?
Isn't that looking at two different planes at the same time?
No.
Planes of axes at the same time. You're saying that the summation of f of x in our original coordinate system is equal to 0, meaning that f2 of x equals f1 of x?
Yes.
But those subtracted don't necessarily make f of x equal to 0.
No, f of x is not 0. No, 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 no. In fact, that's the whole point. All we know that this force and this force is equal, but we cannot have any components along y. Because no matter what the original orientation of these forces are, as long as there is no other force acting along this member, you always end up with these forces have to be acting only along x and being equal. So we define a beautiful concept here. And that beautiful concept, we will beat on that to death, which is the concept of two-force members. Remember that. I'm going to continue on that next time. A two-force member is if you have a member, regardless of its shape, that is pinned at the two ends. Number one requirement. No load acts along that member. Number two requirement. Then, for that member to be in equilibrium, the only possibility is that the forces acting at the two ends have to be equal, and acting along a straight line that connects these 2 points together. We will see the significance of this concept later, and then we'll solve that problem also. Thank you.